All right. In today's lesson, we are going to be exploring further some more properties of graphs of quadratic functions. Okay, so we're going to be looking at what information we can get from the graph of a quadratic function, which, as you recall, is the shape of a parabola. And we're going to use these graphs to solve contextual problems. So this is just an introduction to using quadratic graphs to solve problems. We'll be doing a lot more of this next week after the Easter break. So today is just a nice introduction to using the graphs of quadratic functions to solve contextual problems. And so we are going to have to be aware of the different characteristics of the parabola, such as the vertex, the direction of opening, whether it opens up or down, and if that's a maximum or minimum value, x-intercepts, y-intercept, and of course, the axis of symmetry. So just a quick review for important terms. The vertex of a parabola is the point at which the quadratic function reaches its minimum or maximum value. So if it's opening up, if it's a parabola opening up like this, then it's a minimum value. If it's opening down, then it's a maximum value. And again, this minimum or maximum value is the y coordinate. The axis of symmetry is a line that separates the parabola into two identical parts. It is the x coordinate of the vertex. Put this up here again, so you know that the minimum or maximum value is the y coordinate of the vertex. Not vortex, but vertex. The minimum value is the greatest y value, which is the dependent variable in a quadratic function. And the minimum value, I'll just copy paste this over to save space and time, would be the smallest y value, or the dependent variable, sorry, in a quadratic function. So those are some important terms that we'll need to refer to when we are graphing quadratic functions in Desmos and using it to solve problems. Okay, so one thing we can do is graph some data instead of graphing an equation. So we have some data. So the time would be the independent, so the time would be the x, and the height would be the y. And we could get a graph of this. So I will delete that. We will go into Desmos, and we can insert a table, and we will write out the x values, 0, 0.25, 0.5, 0.75, and so on. 0, 5, and notice if it goes up by a predictable amount, if you just press enter, it will copy them over. If you have differing x values, and that might happen, then don't press enter, press the down arrow. But that's just a little Desmos tip. It doesn't do it for the y. So 2, 6, 8, 8, 6, and 2. And so you'll notice that we have, okay, something going on here, and it looks kind of like a parabola. All right, so I'll maximize this, and we'll zoom in here. We'll make the y minimum -1, and the maximum, we'll make it 5. And x, we'll make it -1, and the max will be 10. Actually, we'll make the x max 2. Okay, so we can kind of see that this expression, the path of the ball, the height is going up to a maximum somewhere around here probably, and then coming down. So if we were going to graph this and determine the axis of symmetry, so we're going to use symmetry to estimate. Remember, the 2 points, okay, they would be equidistant from the axis of symmetry. So for example, if we look at the value of, this is a height of 2, and that's the height of 2, that's a height of 6, and that's a height of 6, and that's a height of 8, and that's a height of 8. So we'll look here then. The axis of symmetry is going to be somewhere between 0.5 and 0.75. It's going to be somewhere between 0.25 and 1, and somewhere between 0 and 1.25. So to find where that would be, you could add the 2 and then divide it by 2. So I'm going to add the first 2 x's. So up at where is 8, so I'm going to add 0.5 and 0.75 and then divide it by 2. And this is just using symmetry. So 0.5 plus 0.75, that's 1.25, and we divide that by 2, and we get 0.625. So if we were to put our line here, a vertical line, x equals 0.625, you would notice then that it would cut the parabola in half. So that would be the axis of symmetry. So graph and determine the axis of symmetry. Again, we can snip this. Paste that and make it a lot smaller. That small. Okay, so the axis of symmetry then equal, we use the 2 x values for the heights of 8 and 8. So it's equal 0.5 plus 0.75, and then we divided that by 2, and that's 0.625. And so therefore the equation always state the axis of symmetry as an equation, x equals 0.625, and that is that. We just found how to do getting the axis of symmetry from, well, using symmetry. So we're not going to do this very often. This is just showing how the axis of symmetry cuts the graph in half. Okay. One interesting point with that would be if we wanted to know at what time does the ball reach its maximum height? Well, the axis of symmetry, x equals 0.625. At 0.625 seconds, that's when the volleyball would be at its maximum height. So how can we conclude that the graph is quadratic? Okay. So the graph, well, it looks like a parabola. In this case, it goes up to a max and then back down. And there is symmetry. Sorry, vertical symmetry. If a horizontal line intersects a parabola at 2 points, can one of the points be the vertex? Again, the horizontal line, if it cuts it at 2 points, it can't be the vertex. If it touches the vertex, it's only going to touch 1 point. So a horizontal line only touches the vertex once. Explain how we can use symmetry to determine the time at which the volleyball reached its maximum height. We already did that. Okay, I did it verbally. I'm not going to write it out here. All right. So we'll begin with looking at an actual example here where we're going to use some graphing. Okay, so we have an equation which we can actually put into Desmos. And again, if you remember from pre-cal in grade 10, intro to applied and pre-cal, f of x is another way of writing y. So we could write y equals negative 0.12 x squared plus 3x. So it's really the same thing. In fact, if we copy and paste this into Desmos, I'll show you. Copy and paste it as is. So I'll just reset the page. You'd still get your parabola. Likewise, if you change that to a y, it doesn't change. So whatever you're more comfortable with. Typically applied math students like the y better, so we'll leave it as the y. I put it in there just as a review back to grade 10. Okay, so the path of the water is an arch. Well, we can definitely see that. There's the arch there. It's a parabola. Oh, it's got a vertex already. We can click on it. X represents the horizontal distance from the opening. So X represents the horizontal distance. And the Y represents the height, which is the vertical distance of the water. So the Y would represent the height. Don't forget units. So when we're labeling, so it's in feet and in feet. So we have to put the proper units in here. So horizontal distance is FT for feet, and height would be FT for feet. Okay, so we have this labeled and we are good to go. Graph is nicely labeled and we have our graph. So the first thing we're going to do is get the sketch. So we've got our Desmos graph. I'm going to zoom out just a little bit there. Maybe we'll do it like that. Okay, so I'll snip it. Move that over there, and again, try to catch the labels of both. So there we go. And that's our graph. We'll copy and we will paste it here. Now it's going to be big, so we're going to adjust the size so it fits all on one page. Make it smaller, and there it is. Oh, okay. So is this a quadratic function? How do we know? So I'm not going to write this out. Clearly, I will write it out. It's the shape of a parabola. So the graph is the shape of a parabola. What's the shape of a parabola? Well, it has a maximum point in this case, and there's symmetry. Okay, so it is a curve that goes up to a maximum and down. That's how we know it is a quadratic. Does it have a minimum or maximum value? How do we know? Well, this parabola opens down. Therefore, it has a maximum value. We could find that out. If we go to Desmos, we could click on it, and as you recall, the maximum value is always the y coordinate, so 18.75. So the maximum value, which represents the maximum height of the water, would be 18.75 feet. Okay. At what point does the parabola start to go down? Oops. How do we know? Well, at what point would be the x distance? So again, we'll go back to our parabola on our Desmos graph, and we'll look at the x coordinate, which is the axis of symmetry. And so at x equals 12.5, it starts to go down. How do we know? Well, as we move to the right, past 12.5, we see the curve start to go down. So that is how we know. So the parabola starts to go down at x equals 12.5. How do we know? The curve swings downward towards the x-axis. So we see the curve start to move down. Now, going back, clearly there would be a restriction, okay? You can't have negative height. So what we would put in here, as you recall from doing restrictions, we would put in our brackets, curly brackets like that, and we would say x must be greater than or equal to 0. And you would see then how it, well, two of them. X must be greater than or equal to 0. And sorry, Y. Y also must be greater than or equal to 0. So again, we want to hang out in quadrant 1. So get used to that, grade 11s, when we are doing contextual situations here. We're always going to be hanging out in quadrant 1. And the way we hang out in quadrant 1 is we add in the extra part, x greater than or equal to 0 and y greater than or equal to 0. And we add it right after the equation. And you can see very nicely how Desmos stops it. So there it is. Now, again, remember, if we need the roots, we're not, oh yeah, we can touch the roots. That's good. All right, so we have all our important points. Basically, as a review, the water starts its arch at 0. It goes up to a maximum height of 18.75 feet and comes back down. The water starts at 0 meters and it moves a maximum horizontal distance of 25 feet. So that's how we are going to be using our graphs to get contextual information, but we're a little bit ahead of the game. So it asks for the axis of symmetry. Well, the axis of symmetry is the x coordinate of the vertex. So it's x equals 12.5. What is the height of the water at its highest? Okay, the height equals 18.75 meters. I mean, sorry, feet. I keep thinking meters. I don't know why. Okay, so again, from the graph, now what I would do is I would delete this sketch and I would put this one in here. This is the better graph. So I would click on all important points, and now we'll snip that. And again, we want to get the both labels of the graph. Copy and paste that there. That graph smaller, so we can see everything. Okay, so now we have all the points. So that's what I would expect to see on your work. Alrighty. So again, we're not doing it by hand. So again, this is your turn. I'll let you give this a try. Okay, you've got another water arch and you've got another equation. Graph it, state the domain. Actually, no, okay. You know what, we'll do the domain and range. So I'll do the domain and range for this example up here so we can see for context. So I'm gonna add this in. Okay, so domain and range in context. So in context means real life. So in this situation, we're talking about water having a height. And when we started our experiment, okay, so we have to hang out in quadrant 1, okay? We have to hang out in quadrant 1, that's fine. But the context, if we look at here, is, okay, what is the maximum height the water reaches and what is the maximum horizontal distance it reaches, okay? It doesn't go past 25 horizontally feet and it doesn't go past 18.75 feet vertically. So in context, the range starts at 0 and it goes to 25 from one x-intercept to the other. So that would be the range, the domain in context, 0 to 25, because it doesn't go further than 25 feet and it starts at 0. Okay, so the domain then, I'll put D for domain, again, square bracket, because it touches it, would be 0, comma, 25, square bracket. That's a domain in context. Range in context, the water for height starts at 0, okay, and it goes all the way up to 18.75 and then comes back down. It starts at 0, it goes up to 18.75 and then comes back down. So the range in context would be 0 to 18.75 inclusive because it touches both points. So square bracket, 0, comma, 18.75, close bracket, whoops, square bracket, sorry. And that would be the domain and range in context. So you can try your turn on your own. It follows this example 2, okay? So I'll let you guys do that. And we will get moving on to example number 3. Sketch the graph of the function. This is just there's no context here. It says sketch the graph of the function, state the y-intercept, any x-intercepts, the equation of the line of symmetry, the coordinates of the vertex, and the domain and the range of the function. Okay. What I'm going to change here is I'm going to put one restriction. The parabola only exists in quadrant 1. Okay, just to put it into context here. So I'm changing that. Make sure that you do show that there. So we'll go through this. So first thing we're going to do, create a table of values and graph. Again, I haven't adjusted this. We're just going to go right into Desmos. So I'm going to create a table of values out. We don't need to do that. We're just going to graph with Desmos. Okay. So we'll go to Desmos and we'll reset the page. Goodbye, graph. Because I'm on here, I'm just going to save time. I'm just going to copy again. F of x is the y. So if you want, I'll just copy the right-hand side of the equation. We'll go into Desmos, y equals, paste. There we go. Oh, okay. So how about we go back and we are just going to, actually, I want to make sure, I'm going to change the equation here. Sorry. I'm going to go negative and go minus x. There. Okay. So bear with me here. I'm just changing this so it hangs out in quadrant 1. So negative x squared plus 0.75x plus 7.5x minus 2. Let's go plus 2. Good. Just bear with me here, grade 11s. I want to make this more realistic for our applied, so plus 2. All right, now this parabola only exists in quadrant 1. Okay, so I'm going to highlight this. Make sure that you have the equation changed when you do your work. I'll highlight that in blue. Okay, so make sure you have the new equation. All right, so negative x squared plus 7.5x plus 2. The parabola only exists in quadrant 1. That's the restriction I'm putting on there. Okay, let's pretend this is, I don't know, the maximum height of a golf ball being thrown up or something like that. Okay, so again, we would want to put our restrictions in. We're right away, we are going to click on the curly braces, x greater than or equal to 0. Click out. Okay, make sure you click out and then go back and click on the curly braces again and go y greater than or equal to 0. Okay, beautiful. Now I'll zoom out. There we go. There's our graph. So we have a y-intercept, we have a vertex, and we have an x-intercept. Okay, so 1, 2, and 3 important points. Notice in quadrant 1, we've only got one x-intercept because the graph goes back. But we only want this. So I'm going to snip that. I didn't label my axes because there's no context here. So that's good enough. Copy, and we'll paste there and make that much smaller. You can see it. So again, when you're making your graph, grade 11s, please have the points labeled on there. Okay, so we have them. We want to see what those points are. That's very important. Okay, good, good, good. So let's begin our analysis. Does the graph open up or down? How do we know? Well, it opens down because the vertex is a maximum point. The vertex is a maximum point. What is the y-intercept? Again, we're going to state the y-intercept as a coordinate pair. So again, it's always 0, comma, whatever the number is, and it was 0, 2. So 0, 2. Again, we always use round brackets for coordinate pairs. Okay, parentheses. Sketch the graph. Good. What is the equation of the axis of symmetry? Well, the equation of the axis of symmetry is x equals whatever the x coordinate of the vertex is. So x equals 3.75. What is the vertex? When we ask that, it's basically asking you for the coordinates of the vertex. So I'll put that, okay, so state the coordinates of the vertex. So I'll put the answer in red. Again, parentheses, so it's just copying 3.75, comma, and we could round to 2 decimal places here. All right, don't take it, no, you don't need to take it further than 2 decimal places, so 16.06. Oh, that's the coordinates of the vertex, and we just did some analysis here. I'm going to add in here, we're going to state the domain. Okay, and we're going to state the range. So we do this for learning. So again, we can see it off the graph. I'll go to decimals. The domain is the x, right? So it starts at 0 and it goes to 7.758, or we can round it to 7.76, and it touches both. So the domain in context, again, would be a square bracket, 0, comma, 7.76. Okay. The range starts, again, we don't start here, okay? We want to look at the lowest, the minimum. So the smallest y value is 0. There it is, 0. So don't think you got to start here because the graph starts on the left. Look for the smallest y value. So it clearly is 0. And the biggest y value is 16.063, which will round to 2 decimal places, 16.06. So 0, comma, 16.06 would be the range for this example, and I will leave that in red. So there we go. We just did an analysis of graphing a quadratic function hanging out in quadrant 1. All right. Solving a contextual problem. So we have a ski jump. So a skier is jumping, and the function is this. So that's obviously their height, okay, versus time, probably. So this would be down here. I'm going to write x is time in seconds, and y is the height here in meters. Okay, so no surprise, no surprise. First thing we should do is get this graph. So we'll go over and plug this into Desmos. So reset Desmos. Okay. I don't like how squished this is. So we can, when we want to scale the graph, it doesn't x, like it, obviously the restriction is quadrant 1. So x isn't going to go past 3.1. So I'm going to make the x between 0 and 5. And the y, I'm not going to make it past 13. So just to keep the x and the y axis, I'll go from -1 on the x to 5 and -1 on the y to 13. And again, why we do this is it just shows, including the negative, just keeps the axes there. Now we're going to state our restriction in quadrant 1. So again, x greater than or equal to 0. Click out, and then click again, y greater than or equal to 0. Beautiful. Got the graph there. Oh no, zoom in there. Okay, so now we're going to, so we'll go from -1, so I said 13, and -1 to 5. Nope. Whoops, backwards. -1 to 5 on the x, -1 to 13 on the y. There we go. The x-axis is the time in seconds, and the y-axis is the height in meters. And we have our graph. Click on the points, y-intercept, vertex, and the root that's there. Sorry, I'm just moving this a bit. Actually, there we go. Just to make the graph fit. Okay. Spent all that time and now I'm not going to use it. Okay, so we'll snip that. Make sure we get both labels. Copy. Paste into our Word doc. Make it smaller so we can see. All right, so let's, happens sometimes. What happened there? There it is. There you go. Okay. Snip it again. It's so much fun snipping all the time. Okay. Well, I'm not going to, there it is, good enough. We know that's 0, 1. So copy that. Must be a Thursday. Okay. Make it smaller and smaller again. Okay, good. All right. So graph the function, we did it. Important points, we have it. Hanging out in quadrant 1, we did it. Label graph, we have it. Determine the skier's maximum height to the nearest tenth of a meter. First thing we're going to do. So A, max height of the skier. How are we going to do that? Well, we are going to look on our graph and find what the maximum height would be. It would be at the vertex and it would be the y-coordinate. So we would click on the vertex. The y-coordinate is 12.48 meters. So the max height is the y-coordinate of the vertex. Therefore, max height equals 12.48. Make sure you put units, meters. So that would be your final answer right there. That's the maximum height of the skier. Let's say that question was, at what point does the skier hit the ground? Well, that would be the x-intercept, where it hits, like it starts at 1 meter and it goes down, and that would be the time at which the skier completes the jump. At what height did the skier start? Well, it would be the y-intercept. The height is 1 meter, goes up to 12, and then down to 0. Okay. The second question was, state the range of the function. The range of the function, again, the minimum y value is 0, the maximum y value is 12.48, and it touches both inclusive, so the range would be 0, 12.48, square bracket on both ends. And we just solved our first contextual problem with the quadratic. So I hope that makes sense to you. You can look through what we did. If you want to try this question here, your turn. Okay, so you can try that, going through the same process we did. And you've got some homework questions. If you could have that done for Thursday, sorry, today is Thursday. If you could have that done for Tuesday after Easter weekend, and there will be a concept check for this on Thursday. So I wish you the best of luck. I hope you have a great Easter, and I hope this video was helpful.